Okay, so firstly, thanks, Ramon. Thanks to all the organizers for the invitation to this beautiful part of Germany. With I also discovered very beautiful wine yesterday. I discovered apparently they have good wine. So today I want to talk about Majoranas in artificial Kitaev chains, and essentially there are three things I'd like to talk about. So firstly, an introduction to what Kitaev chains are. We heard a little bit yesterday about the basic phenomenology of Kitaev chains. How do we engineer them? And in particular, I want to talk about engineering them in two-dimensional systems, so two-dimensional electron gases. So I'll be talking about systems which you see here, which are basically confined electrons in 2D systems, which are proximatized by a superconductor. So we're talking about superconductor semiconductor hybrids in 2D systems. How do we engineer them? Then how do we study them? So how do we actually look at the properties of Majoranas, or how do the properties of Majoranas manifest themselves when we're looking at these Kitaev chains? So before going further into the talk, I want to talk about the kind of devices that you'll see, the kind of systems we work with. So you can see this 3D schematic of, you have a two-dimensional electron gas, and in this spirit of, for example, Alex's talk. So we don't work with 50 by 50 arrays. We just work with two quantum dots. You can confine electrons where you want. And I will be talking about systems with two dots. So you have two dots which are coupled to each other, but the special thing is that they're not just coupled via tunneling, which is common. You can couple two quantum dots via just single electron tunneling. But they're also, this superconductor plays an important role. You can actually have different kinds of coupling because of this superconductor. So we will talk about these hybrid systems, and I want to take you through how we can actually take a simple system like this, which is just a double dot. People have studied forever. You introduce a hybrid section in there, and you actually can create Majoranas. Okay, so with that said, let's sort of move forward. Before I go on, it's an effort that has been ongoing for quite a few years now. The work I will show today is mainly led by Bas and Ching and these two master students. And we, in the past year or so, we collaborate actually a lot with people working on nanowires. So for example, Alberto is here today with a poster. So it's now becoming a concerted effort. So I will quickly go through this, just sort of a general motivation for Majoranas. You have qubits, they're prone to errors. You can try to make your system cleaner, right? So this is, for example, isotopic purification of silicon, or you can do error correction. And a lot of the push for this study of Majoranas is that, can we find another route, which is, can we actually create hardware which is somehow intrinsically protected, right? So it's protected from local perturbations. Can we find a system where we can encode information in something which has this kind of protection? And this is sort of where a lot of the motivation to study Majoranas comes. And there are many different ways. We heard about fractional quantum Hall, right? That's one way that you can get to non-abelian physics. There are also different approaches. So for example, one that became popular is, let's take a one-dimensional system. Let's put a superconductor on here. So we effectively have a one-dimensional hybrid system. Let's turn on a magnetic field, and you should have Majoranas at the edges. It sounds very simple, and at the time when these proposals came out, more than a decade ago, people had access to these wires. People could make hybrid structures, and there was a lot of effort. These were some of the first kind of devices. So those who may not be familiar with these kind of devices, the idea is essentially, you have the wire here. This is your hybrid segment, and then you have these gates, and these gates basically alter your electrochemical potential. So for example, if you tune this to a negative voltage, you can create a barrier here, and you can do a local density of states measurements, and you will see a lot of these measurements as we go on. So what are some of the basic properties of these Majoranas? Well, firstly, they, by definition, appear at zero energy. So they live at zero energy. They come in pairs. So they always come or are destroyed together. And this idea about topological protection actually comes because you, in a way, store information non-locally in these spatially separated Majoranas. So the larger the separation is, actually exponentially, you get more protection. And I think you heard about braiding and exchange statistics. That is just generally true for anionic particles. You can, in principle, do protected operations. So this sets the stage a little bit with Majoranas and the motivation and why people wanted to study these. And then there's been a lot of research. And what I want to just show here, this is not representative, is that this probe of the density of states and seeing something at zero energy, there were the first experiments, and then it became more and more ubiquitous, and you could see many, many regions where you see enhanced conductance at zero energy, which reflects your density of states. And I wanted to summarize, I think many people here would agree with these, maybe some don't, is that I think there are many, many signatures of Majoranas. There are things that could be consistent with Majoranas, but if we want to go back to something that is actually topologically protected, and that you actually have a topological phase, showing this, I think, is still missing. But on the other hand, what has happened is that there's been in the past decade huge improvements in fabrication methods, in materials, and these actually have played a very important role in, for example, the results I will show today. But I think in these sort of one-dimensional systems, I think essentially disorder is still a limiting factor. So you have high disorder, and not only is disorder bad because you have fluctuations, but it can be even worse because many things that have to do with disorder can actually look like Majoranas. So that makes it 2 times worse. Okay, so Kitaev chains. So Kitaev had this model in 2011, which was a toy model, and these are sort of the origins of Majoranas. Is you essentially take fermionic sites, and then what you can do is that you can introduce 2 kinds of coupling, a T and a delta. So we'll go into what T and delta are later. So the mu is the on-site energy, and this is a single electron process. So you exchange single electrons between 2 sites. And delta is a process where you exchange 2 electrons, not sequentially at the same time, simultaneously exchange 2 electrons. And if you go through this math, the whole idea behind the Kitaev model and what is the connection between these fermionic operators and Majoranas is that you can essentially rewrite the fermionic operators as Majorana operators. So that sounds a bit like just a simple basis transformation, which it is. But then when you recast the Hamiltonian in terms of these Majorana operators, you get 2 interesting limits. The first is a trivial one. So you can decompose a fermionic operator into 2 Majoranas, which means that this is essentially me looking at each of these sites and thinking of them as 2 Majoranas. So they're just coupled on site. But the interesting part, and this happens when there's essentially T and delta are 0. So these hopping terms are 0. But now what happens when T and delta are the same is that you have a pairing between neighboring sites. And this is sort of what is depicted with these lines. And you'll see some of these pictures again later, is that this means that neighboring sites are coupled, and as a result, you're left with these 2 isolated Majoranas. So this is, in Kitaev's model, this is the situation when you actually have a topological system, and this is when you have a trivial system. So I think this part is important because the rest of the talk is basically about what these T's and deltas are, how you tune them, and what are the signatures when you go through this trivial to topological transition. Okay, so that was 2001. About a decade later, there were some concrete ideas. Okay, so we have these sites, and you can think of sites. The easiest way to, well, one of the ways to create them is just you make quantum dots. So your sites are quantum dots. And how do you mediate this 2 electron process? Is you use Cooper pairs. So you use superconductors. So if you have 2 dots that you can actually couple via a superconductor, you could in principle get a T and a delta, and you could think about trying to tune to the regime where T equals delta. And this was really, I think, the first concrete proposal that said, you could actually make Majoranas this way. So we've been talking about these T's and deltas a bit more concretely. I won't go into much detail what these processes are. So T is, like I mentioned, is just a single electron process where you can exchange single electrons. And it's called elastic co-tunneling, or ECT. And delta is actually a process called cross-Andreev reflection, or kind of equivalently Cooper pair splitting, where you can basically take a Cooper pair and put it into quantum dots, or you can take 2 electrons from 2 quantum dots and put them into your superconducting condensate. And this is called cross-under reflection. So microscopically, these are the 2 processes that we need to control. Okay, so I think 2 more things that I want to talk about is that the first system I'll talk about, you saw 2 quantum dots, so I want to just talk about a 2-side system. So let's not talk about an infinite system, let's simplify things. Let's talk about a 2-side system. So what we learned is that you have these 2 fermionic sites. They have 2 kinds of hopping, the ECT as we call it, and the CAR. And now I told you that we can recast the entire Hamiltonian in terms of Majorana operators. So this picture actually transforms into an interesting picture that looks like this, and I will use this sometimes. So what you see is that you can decompose every fermionic site into 2 Majoranas. That's why these half circles. And you can think about all the different couplings you can have between these Majoranas. So for example, this has a T, again, I won't go into too many details, but this coupling here is T minus delta, this is T plus delta, and this is the chemical potential. This is the on-site energy. So if you sort of keep this in mind, you can again think of the different limits, right? So this is the trivial fermion, which means that there is no interaction. T equals delta equals 0, right? So this is just think of essentially a simple basis transformation. Then you can think of localized Majoranas, which means that you now satisfy this condition where T and delta are non-zero and mu equals 0, so you cut off these guys. So these 2 don't talk to each other, and you can see here that this goes to 0, this coupling, and this is what actually gives you these isolated Majoranas. So you now, when you reach that, you actually get these isolated Majoranas on the 2 sides, even for 2 sides. The other important thing is how do we think, or when we think about Majoranas, we think about perturbations, right? So what if I agitate one of the dots, right? So for example, what if I change the chemical potential of one of these dots? What that means is, again, if we think of the diagrams, is that I'm making a connection here. But making a connection here, if I'm agitating just one dot, changing the chemical potential, has no effect on this Majorana. And this is basically the idea of protection to local perturbation. So I can agitate one side, but nothing happens here. So I think these concepts will be important when I start showing you data. So I think the 2 important things are this condition here and what happens to local perturbations. Yes?
So you are saying that as far as the Majorana, their protection is more strong, the more their distance is more.
Yes, the more, and in this case, the more that's number of sites.
Yeah, but how is this from the equation I can get?
Like what happens in terms of the protection? Why does the protection increase in terms of size? I think there you basically have to think about where do you go from a discrete structure to a band structure. So essentially, when you increase the number of sites, you basically have these bands, which then give you this protection. And then you have a concept of an actual true bulk. But I'll come back to a little bit of it when I compare 2 and 3 sites. We'll talk about it. Yeah. Okay. So there's one last ingredient before I go on to experiments, which is I said that the game is that we have to be able to tune T and delta. So if we think about bulk superconductors, you can think about suppose I had a bulk superconductor, I had 2 quantum dots and 2 sites. The ability to do this cross-Andreev reflection depends on the coherence length of the superconductor. So if you want any significant tunneling between these 2 dots, which is mediated by the superconductor, you have to have, for example, very narrow superconductors, or you have to, but that's point 1. Point 2 is that it's fixed, right? So once you have a certain dimension, a certain ratio of the coherence length to the actual device length, that's fixed, so you cannot tune it. But what's really interesting is that you can actually not use the bulk superconductor, but you can use what is called an Andreev bound state, which is essentially a hybrid region, so it's a proximatized region. And without going into too many details, is that this region is actually gate tunable, so you can change the energy of this. And if you go through the math, what you see is that the amplitude of the ECT process, the single electron process, and the amplitude of the CAR process have different functional forms. And these U's and V's here are basically a description of the Andreev bound state which has an electron-like component and a hole-like component because it's connected to superconductivity. But what is important is that when you look at these two things, you can actually firstly just do the math, and you can see that the probability of CAR, as you change the energy of your André bound state, so you have a gate that changes the energy of the André bound state. This is the energy of the André bound state. As you change that, what happens is that the amplitude of the cross-André reflection goes up, reaching a maximum at 0 energy. And the ECT has a different dependence. So again, I think Alberto is in the audience. He did one of these first experiments, which were really, really nice on wires, where you actually see this. And the point is that these are the places where you satisfy this T equals to delta condition. So the take-home message is that if you have a gate tunable system where you can tune the André bound state, you can actually get to situations, these points here, for example, where you get T equals to delta. Okay, so we have two sites and we have an André bound state. We have a way to potentially tune T and delta. So just to sort of set the stage for, what are some of the minimal requirements? Firstly, you need spin polarized dots. So we have to apply a magnetic field to spin polarize our dots because the Kitaev model is a spinless model. So you have to take away spin degeneracy. Second I talked about was T and delta. You should be able to control them. And you need spin-orbit coupling. I won't go into detail. I glossed over the fact that the Kitaev model actually assumes a p-wave pairing. So you have to have some kind of non-spin conserving processes, and the spin-orbit coupling actually is the thing that allows you to have this. But we can discuss it later. But these are the three main things that you need. And I already showed these devices. I won't go over this again, but you have a 2D gas, standard way to make gates. So this is where your quantum dots are. This is where your André bound state lives. And for example, this gate tunes the energy of the André bound state. If you look at an SEM image, what it looks like is, we have multiple layers of gates, in this case 2, and we have these big gates that form essentially a quasi 1D channel. And then we have this aluminum strip which proximatizes this region, and these are the two dots. So it's fairly simple device geometry. And what do we measure? The typical measurement that we do is we either look at, either DC current with lock-ins, or more recently we do reflectometry to make things go faster. But the point is that it's a 3-terminal measurement where we simultaneously look at the left and the right. So we're looking at transport simultaneously at the left and the right. Okay, so I spoke about quantum dots. I spoke about André bound states. So some of the basic checks that you can do before you sort of go looking for Majoranas is look at André bound states. So let's imagine that these dots don't exist. But I can use these gates to form a tunnel barrier. So I can just look at the local density of states in this hybrid region. And I can look from the left, and you see some kind of a pattern where you see some kind of a modulation of André bound states. But the important thing is that if you want to mediate coupling between these two dots via the André bound state, you better make sure it's an extended bound state. Otherwise, there's no hope of mediating coupling. What this means is that if I look from the left and I look up from the right, I should basically see exactly the same density of states. So this is one check you can do, is you can look from the left and the right simultaneously and see whether you really have a system there, an André bound state that can potentially mediate coupling between these two quantum dots. And the second thing is, of course, can you make quantum dots? And here you see some Coulomb diamonds where you're basically changing your dot occupation 1 electron at a time. So we can do these things. These basic ingredients seem to be there. But now how do we go from here? So we have dots, we have André bound states. How do we make this Kitaev chain? So how do we go to these Majoranas? And I want to go back one more time just to appreciate a little bit the simplicity of this Hamiltonian. So you can take this two-site system and you can explicitly write down the Hamiltonian. And what you see here, so these are the eigenstates, right? So you are either in the even manifold. When you're in the even manifold, means that the total number of electrons is even. And there, not surprisingly, the coupling mechanism is delta. It's this 2-electron process. If you're in the odd manifold, the coupling mechanism is this single electron process. And this is really a simple 4x4 Hamiltonian, which you can analytically actually solve. So what happens in transport? So how do we measure? So what is the repercussions of this Hamiltonian when you look at transport through this double dot system? So what you can do is, because you can divide this into even and odd manifolds, you can actually look at this. This is effectively a phase space, right? So where am I in the 0, 0 occupation? In the 1, 1 occupation, so these are even. And these are the odd occupations. So depending on the ratio of T and delta, so whichever is greater, what you will see is that when I sit at mu1 equals mu2, so that's 0 chemical potential, in one case, my ground state is odd. So when T, so basically when T is the single electron process, when that dominates, your ground state is odd. And when the two electrons, so the cross and the wave reflection dominates, your ground state is even. And right in the middle, where you have this condition where T and delta are equal, you get what is called the Majorana sweet spot. It's also referred to as the poor man's Majorana, coined by these people here. I'll tell you why it's called the poor man's Majorana later. So the idea is that when you look at transport, if you're looking at a dot system, you are actually only sensitive to transition. So when you change your charge by 1, there is a certain charge degeneracy. So these are charge degeneracy points, and that's when you have transport in your system. So you're allowed to actually transfer electrons between dots. So let's look at our system again, just to remind you. So we have a left dot, a right dot, and our tuning knob for the T and the delta is this gate here that controls the gate voltage. So we can actually, so I showed you this picture here. We can actually measure. So now we're doing actual measurements. We're changing the gate voltage, so the energies on the two dots. And we're looking at what happens to the transport. And these lines here are high conductance, which means that these are the charge transitions. So we can look at this. And what is important, I want to point out, I mentioned we always measure on both sides together, because this is important. We have to look at what is happening on both sides simultaneously. So that's why you see this LL and the RR. So you see the left conductance, you see the right conductance. You can change this number, so this gate voltage, which is our tuning knob, and you can go to the other extreme. And what you see is that this basically, what is a diagonal like this becomes a diagonal like this. And this takes you to a situation where here, you're now sitting in the even ground states. So you go from the odd ground state to the even ground state, and naturally in the middle, you have a degenerate ground state here. And this, experimentally, is exactly where you hope to see Majoranas. So what we do is we tune to a situation like this. And then the first thing you can ask is, OK, I tune here. Let me sit here. Majoranas live at 0 energy. What happens when I look at the system from both sides? And you see an enhanced conductance at 0 bias. In fact, these side peaks from this, you can actually read out exactly what these T's and deltas are. I won't go into that. But this distance actually tells you what the effective coupling between the dots are. So this is step 1, right? So you see correlated 0 bias peaks on both sides. But now I want to come back to what local perturbations are. What are local perturbations and how we define them? So the experiment that we do is, let's change one, in this case VQDR. Let us change the right dot. So we change if you go along this axis, we're changing the chemical potential of the right dot. And OK, the right and left are reversed here, but it doesn't matter. But what that means is that I now start introducing a coupling here, but it should not affect the other dot. So the experiment that you see here is I change the dot, the left dot, and I'm looking at a bias spectroscopy, right? So this is as a function of bias. So you can think of this as the density of states. And this state actually remains at 0 energy. So that's point 1. But point 2 is that we can also go away from the sweet spot, which means that we can change both the dots simultaneously. So I'm not changing now one chemical potential. Now I'm really disturbing my system. I'm simultaneously changing both, detuning both the dots. And here what you expect is, and this is where the name poor man's Majorana comes in, is that you very quickly lose this 0 energy state. And the point here is that in a two-site system, this energy state, you lose extremely quickly. As you increase the number of sites, the region in which you have this, so the protection you have, this increases more and more to detuning. And this is actually, so in fact, this goes quadratically if you have 3 sites, it goes to the power 3, et cetera, et cetera. And this is why these states, they have all the properties of Majorana, so in terms of operators. And next talk from Ruben, you'll hear how you can do fun experiments with these 2-site systems, but they don't have this topological protection that you, for example, need for a topological quantum computer and things like that. Okay, so that's good. We can look at 2 sites, and here I want to actually mention that a lot of this work was motivated by work that was done in wires in Delft. So what I find remarkable is that historically what happened is 3 or 4 years back, 3 years back, I think, some of these results were coming out on wires. It's like, okay, this looks cool, let's try it. And it worked. So if you look at let's try it on 2 decks, and it worked. And if you look at the pictures, it's remarkable that you actually see the same physics, and it's nice that, physics works. It doesn't care about platforms, and you can do the same physics irrespective of platform. There's also been efforts recently on wires where, we were talking about these quantum dots that are coupled via superconductor, studying how things change when you actually hybridize very strongly to the Andre bound states. So please also look at this work on wires. Okay, so I think it's timed proper, so it's a little less than half an hour, no, right? Yeah. Okay. So part 1, I think, is about these 2-site chains. We can make them in 2 decks, and why we want to make them in 2 decks will become clearer. I mean, you can have these discussions about scalability and this, that, but for me personally, what I like about 2 decks is the flexibility. So if you want to study physics, there are many different ways you can probe it, and I will give you an example soon. And this Hamiltonian, this 4x4 Hamiltonian is extremely simple, and you can actually tune every parameter in that Hamiltonian and see whether it works out, whether things behave, things evolve as they should. And like I mentioned, whether it's nanowires, whether it's 2 decks, you can look at multiple platforms, multiple devices, and the physics is always the same. So by multiple, I mean, I think our success rate is 100%, which is 8 or 9 out of 9 2-deck devices. So if our gate don't break or something, you always can tune into this regime. And I think that from a physics point of view, I know people have been wanting to study Majoranas. I don't know whether you can make a quantum computer with this, but I think it's a very fun way to start looking at Majoranas more systematically. And again, Ruben will talk about how you can take these 2-site systems and actually start thinking about doing things like braiding. And looking at the first sort of rudimentary qubits where you can actually start to use Majoranas. Yes? Mm-hmm.
And then you simply say something about the spin orbital coupling, and then you separated this fermionic operator into Majorana, which is completely true.
Mm-hmm.
But the spin degree of freedom.
Sorry, I did not mention, this is all done at a finite Zeeman field. All the experiments are done at about between 100 and 300 millitesla, and that's enough to spin polarize our dots.
You are saying that you are freezing the spin degree of
Yes.
freedom, and you only have just tunneling.
Yes. Yes.
But this is very important, right?
Yeah, no, I should have mentioned that you need a Zeeman field. So all of these measurements are, yeah, thanks for pointing out. No, thanks for pointing out. So all of these measurements are done in a field because you need a spin polarized dot. And the reason sort of we like the materials like this indium, in this case ternary indium antimony arsenide, is that G factors are huge. So you can basically apply somewhere between 100 and 200 millitesla, and you have full spin polarization of your systems. So the G factor is about somewhere between 20 and 40, something like that. So yeah, thanks for pointing out, is that we always apply a magnetic field in order to polarize the dots, yes. Okay, yeah, so there are very fun things that one can now start thinking about doing. One of the things, these are a few of the things that we are working in the group. I don't want to go into details, but essentially a lot of the efforts in the group are now, okay, if we can make these, if we want to go towards anything, whether it's like some simple braiding experiment or whether it is about doing, well, anything that requires parity conservation, we need to know what the parity lifetimes are. So we're trying to now study using things that people have been doing, for example, in spin qubits, use charge sensing to actually try to figure out what is the parity lifetime of these states. And another obvious question is, okay, you talked about 2 sites. What about what happens when you do 3 sites? So this is the logical extension, and I want to spend in the next 10 minutes or so talking about our work on these 3-site systems. So I spoke about the 2-site systems, and these are called these poor man's Majoranas. You have this fine-tuned sweet spot where T and delta are equal, and the chemical potential goes to 0. Now, what changes actually in the 3-site system? Not so much, but a few things which are actually quite important. So the first is that, when we think about topology, you always think about bulk edge correspondence, or there's something at the bulk, there's something on the edges, and in a 2-site system, there's no concept. You cannot even imagine the concept of a bulk at an edge. So the minimal system where you can start thinking that, okay, if I really have localized wave functions on the ends, are they really localized? Can I really make sure and check in the middle and see whether there is no wave function that leaks in? So this is sort of the precursor where you can think of the bulk of a system. That's part 1. Part 2 is now, here there was this one superconductor, and now there are 2 superconductors, which means that there is a phase difference between these superconductors. And these hopping amplitudes, I wrote them as real quantities, but in reality they're imaginary quantities. So they have a phase dependence. So what is the consequence of having a finite phase difference between these two superconductors? And so this is, again, I want to point to Alberto, who has a poster. There's some beautiful work on wires, where point 1 is, this goes back to this question about protection. I'm not going to go through, explain this slide, is that you can actually directly see when you go from 2 to 3 sites, your protection to perturbations actually increases. And Alberto can talk more about that. But there are 2 specific things I want to talk about. Is firstly, if we look at the density of states. So let's look at the density of states simultaneously at all of these 3 places. And this is a very simple effective model simulation. So GLL is the conductance, effectively the density of states. When I go into the sweet spot, I should see that I have 0 energy states that lie on the edges. But if I look in the middle, it should be a gapped system. So density of states should go down. So on the edges, and this has to happen simultaneously. So in order to do this, actually, and this is one of the reasons why I said that I like the flexibility of 2DEGs, is that all we need to do is we need to basically put in another probe on the middle dot. So we just change our device geometry, how we make the gates, so that we can probe this middle dot as well. The other thing is the influence of flux. And these are, again, some simple simulations where you see what happens on the left, middle, and right as you change the flux. I think the most interesting is actually in the middle, because this is also quite intuitive, is that if you're at 0 phase, your middle is gapped. And simultaneously, if you look at 0 phase here, you have edge modes. But the moment you start to change the flux, what happens is that this gap, this bulk excitation gap, closes, and it actually closes at pi. So this is important, because if you don't have any control over the phase, you could be sitting anywhere here and not know exactly where you are in this phase diagram. So these are the 2 questions we wanted to answer. And now what our device looks like, this is, basically we extended, we now have 3 dots, 2 superconductors, and these 2 superconductors are actually connected in a flux loop. So schematically, we have left, middle, right. We can simultaneously probe left, middle, right, and we have this flux loop. Okay, so how do we tune this system? It's actually exactly what you saw with the 2-site. So what we do is we just work in pairs. So we look at the left and the middle. So we take these 2. We again look at this T to delta crossover. And so now we have formed these 2 Majoranas here. And this is what you see here. So then we sit here, and we always check to make sure all the correlations between the left and the right. And this dot is off resonance, which means that it does not play a role in the transport. So we're looking at these 2 dots. And then you play the same game. So you've tuned this up. You have your middle dot somewhere. And then you look at the right side, and you do exactly the same experiment, and you go to a sweet spot. So now, in principle, you have all these 3 dots tuned so that the pairwise coupling satisfy the t equals delta criteria and mu equals 0. So then you can ask the question, okay, if I do this, what happens? Now let me do spectroscopy. So let me look at the left side, and I see a zero bias peak. Let me look at the right side, and the thing that this was, well, in some sense not so surprising, but what was really nice is that when you look in the middle, you don't see anything. So you don't have a leakage of the wave function into the middle. So what you see is that the wave function actually does decay, and you see the density of state is significantly lower in the, let's say, the bulk of the system. So this is I think, a nice start. And then what you can think about is, okay, I said the flux plays an important role. And how do you see this? So these are, again, the other simulations I showed you. I come back to these pictures with these lines and the couplings. Now there's a difference is that delta has a phase component, which means that this t plus delta and this t minus delta, you can actually tune these couplings with a phase. What that effectively means is that zero phase, only this coupling is relevant, which means that you have these isolated Majoranas. But what phase does, and you can see this from these pictures, is that let's now take the phase to pi. So when phi equals pi, you have a completely different situation where you essentially have one, it's called a delocalized Majorana here, and these three here. So one way to think about it is that you shifted a weight of your wave function from these two to leak into the middle. And this is, for example, what you see here is if you look in the middle, there's nothing. There's no density of states. But at pi, you have a wave function that leaks into the middle, and you lose any concept of topology or Majoranas. So the experiment that we do is we stay at that sweet spot, and then we change the flux. This is just raw magnetic field units because there are offsets, and we don't know exactly what the offset is. But what you can see is that, at least qualitatively, you can see exactly what you would expect is that in the middle you see a gap at zero phase, and then this gap closes and then opens as a function of flux. So I think this is. I think I will skip this part. We can talk more about this. It's the ideas about what is protected and what is not. Really cares about flux. So we showed these detunings. If you detune the left, the right doesn't care. So there's absolutely nothing that's happening. But if you kill this gap, this excitation gap, then you don't have any protection anymore here. So you basically, as you detune, you completely lose your protection. But let me skip this part. Okay, so I think part two is essentially, I think that if we want to study Majoranas, I think these are really, really great. This is a great platform to study Majoranas, mainly because of I think the reproducibility and of the fact that it's actually a very, very simple system, and you don't have to play around with funny simulations and this, that. It's a very simple Hamiltonian. And especially with 2DEGs, I think it's nice because you can think about interesting experiments. I gave you an example of, how can you really look at the bulk? This I think has been an outstanding question, is that how do you look at the bulk in for example, a 1D system? So with this, I would like to stop, and thanks a lot.